As other guys joins, let's start the session. Let the other students join in between. So it's already 3 o'clock, then I think I will start the session from today. So, very good afternoon to one and all. Welcome you guys again on this live interactive session on Mass Transfer Operations 1. This course is being offered on the NPTEL SWAYAM portal for the online course certification on Mass Transfer Operations. So basically, we've already gone through the week 3 live interactions from dry run to week 1 to week 2 to week 3. This time we are going for the week 4, and as soon as we are proceeding with the weeks, the complexity of the course is also going to be increased day by day. So we just brush up what we did in the last week, and we'll begin with the this week topics and some numerical questions to care about. So before we proceed, I'll just it's a mass transfer operation course on NPTEL SWAYAM portal, and this course has been offered by Professor Vishnu Pada Mandal, who is a professor in the Department of Chemical Engineering at Indian Institute of Technology, Guwahati. And a little bit about myself is that I am teaching assistant. I am Rajput Shubham Ajit Kumar, and I am permanent scholar in the Department of Chemical Engineering at Indian Institute of Technology, Madras. So, like I said, I will be teaching assistants for the entire duration of the course from July to November or October till the tenure of this course, and we'll be having these live interactions every weekend on Saturday from 3 to 4. So those who will be joining new to these live sessions, we have not done prior three live interactions. It's just like you can ask any questions or doubts similar in the live interactive session related to the assignments or some of the topics. So what I do is that I will just use to brush up some of the topics through the week content, and then we'll solve some of the problems related to the week content, so that it will help you out guys to solve out some of the problems for the assignments that has been posted on the NPTEL SWAYAM portal. So it's better to go through the week content or the topics that have been covered on the NPTEL. Plus, apart from that, we'll solve some of the questions like what we are doing from the prior 3 weeks. Okay. So before we proceed, this is the week 4. Like I said, already week 3 semi ended, and we have gone through some of the dimensionless numbers or dimensionless quantities, and some of the terminologies related to them, mass transfer anomalies like Reynolds number, Prandtl number, Schmidt number, Sherwood number, and how they can be used in order to solve some of the numerical problems related to mass transfer. So what I will suggest is that it's better to go through the week contents thoroughly, because it will help you guys a lot to solve some of the questions directly. Straightforward questions will be asked in some of the with some of the concepts, and this like dimensionless quantity numbers are one sort of them, so you can directly grab the marks from them within like 1 or 2 go. For the week 4 content, what we have for the week 4 is that the fun is the mass transfer theories. So there are three to four mass transfer theories. This is two-film theory, penetration theory, surface newell theory, Lewis-Whitman theory. So all these theories have the different concepts and how you can use the mass transfer related uh, uh, concepts in them and how to arrive at a particular answer. So it's been much more like the film theory and how the transfer of mass happens in the film. So there are different scientists who perform like different. They have to try to develop their own theories, out of which these four are much more well known. And in undergraduate studies, we usually study this four. It's the two film theory, penetration theory, surface renewable theory, and Lewis-Whitman point theory. So this is what this week has covered. First is the mass transfer theories. Another one is the interface mass transfer. So how the interface mass transfer plays a role in some of the in the real world problems. Also there are mass transfer. There are so many processes which involves mass transfer. But how this interface mass transfer? So interface mass transfer is nothing. It's playing a role. Suppose we here A and B. So there is an interface between them. So what happens at the interface? So you can surface as interface. So there is a phase between them. Okay, so what happens at this interface and how the mass transfer happens as an interface. So that is what we have covered in this week of week 4. And the interface mass transfer and material balance for an operating line. So this operating line is nothing, just the, if we have gone through the lecture notes, you might have seen the gas absorption column. So this side, yeah, and this. So if you consider gas absorption column, what will happen is the gas will flow from here, that is y1 to y2, and liquid will flow from the counter current flow, that is x1 to x2. Similarly, you can type as g1, g2, L1, L2. So in the basis of this, we have seen some of the like mass transfer material balance is happening in the gas absorption column. This is somewhat like that's what I'm saying. So what we assume is that you want to absorb some specific amount of gases while passing through a liquid solvent in the countercurrent flow, so that it can be absorbed and selective amount of gases can be sent out, so that it can be used for the one sort of gas absorption, like particular like specific absorption of the solute or the molecules. What you want to use, like suppose you carbon monoxide you want to absorb, you can use gas absorption column, and apart from that, in order to absorb carbon monoxide, you will use some liquid solvent. That is what I am mentioning in the countercurrent flow mode. And the last one is the number of the ideal stages in countercurrent operation. So the countercurrent and co-current. So co-current is, I'll say in the other slide. So one is counter current, another is co-current. So counter current is in opposite directions, whereas co-current is in parallel direction or in same direction, you can see. Or parallel direction. Okay, so this is what counter current and co-current. So what you're saying is the number of the ideal stages. So ideal stages just we are considering because it's not the real problem here what you are discussing. So ideal is the number of ideal stages that is generally been required, and it's an ideal concept because it's you can't consider any amount of the, what you can say, the noise happening from the outside real world to the problem. But if you go to the real world problems and the real industries and the mass transfer operations, like in the distillation columns, there is no ideal stages. That there are the real stages and the real number of the stages required to separate the rectifying and the stripping section. That is parts of the distillation column and the field section. So this is what we are considering as number of the ideal stages in the countercurrent operation, and the graphical and the algebraic methods to solve that point. Okay. So before we proceed, we will just say what has been covered is the force of mass transfer theory, the two film theory. Two film theory, penetration, third is surface renewal, theory, and the fourth one is Lewis-Ritman. Okay, so I think you guys have already went through all the like the concepts of the two film theory, penetration theory, and a surface renewal theory. What I can say is that one is the penetration, like two film theory is a common one, but in the case of the penetration theory, what is seen that the gas bubbles are the liquid droplets which are coming to the surface, and there is initial intermediate contact between the gas and the liquid, and this is the case is considered to be the exposure time is theta. So we can explain this as kT is equal to 2. So this is the equation of the penetration theory, that is diffusivity of air respect to how this comes above the surface and how this we can relate it with the equation. So this is the equation for the penetration theory. This comes after the derivation of the penetration theory. So there are so many things and so many concepts to be learn about. Another is the interface mass transfer. This is about the theories. Another is interface mass transfer. So the theoretical principle of diffusion, or we can say the principle of diffusion of the gases and a mass transfer from one point to the another point in a single phase or in the homogeneous system. So what is happening at the interface? So most mass transfer operations in the practice involves transfer of one or more solute or the molecules between the, what you can say, between the two insoluble phases. For example, if you consider the absorption of ammonia or the removal of ammonia as a byproduct as coke on gases by the water. So there are so many different things that is happening here, and what is happening at the interface. So this is somewhat like removal of the ammonia from byproduct coke over the gases by water. or we can consider them own gas. So there are different type of gases. So like I said, own gases by water, and there is also purge gas, and how these gases are. So these are different related terms we are going to study in the later course of time. So we'll go to another concept, what is called as the Raoult's law, and you can say, like we already studied two laws of mass transfer. There is fixed first law of diffusion and fixed second law of diffusion. Similarly, there are two different laws of which are terms as Raoult's law and Henry's law. So what is Raoult's law? So for an ideal, if you consider for an ideal gas, liquid, or vapor liquid mixture or system, okay, the equilibrium relationship is given by the Raoult's law, and it is written as partial pressure of A equal to Xa into P, where P is the saturation pressure. Or you can consider PA star equal to the equilibrium partial pressure and Xa is the mole fraction of the solute Xa, then the solute A in liquid, and Pa is the vapor pressure of A at a given temperature. So this is what we term as a Raoult's law. Okay, so there are different terms, and the solution that behaves ideally follows the Raoult's law. So the solute and the solvent's molecules have similar size and internal forces, and the excess volume of mixing is zero, and the heat of mixing is zero. So these are some of the assumptions that have been made for the Raoult's law, and you guys must remember these assumptions, because by solving some of the numerical problems, this might come to a point actually. And another one term is known as the Henry's law. So this is what I mentioned. Oh, just 1 minute, guys. My system is lagging. Okay, right up here also I'm having some major problem with me. So another one is like this is Raoult's law. The another one is known as the Henry's law. This is Raoult's law for gases. Now we are having Henry's law for liquid actually. So the equilibrium data from non-ideal gas liquid. Equilibrium data from many non-ideal gas liquid system at low concentration can be expressed by with the help of Henry's law, and it is given by, that is PA is equal to H into XA. So HA here is known as the Henry's law constant, where HA is the Henry's law constant. And also this, that the HA is mostly a function of temperature for given solvent solute pair, is a strong function of the temperature. Okay, so this is how we discuss like two different laws, Raoult's laws and Henry's law. Now what we'll do is that we'll go through some of the numericals. Like first we'll start with some of the basics, uh, and how to arrive at a particular thing. So here what I have for these things. So like what we discussed as the two film theory, penetration theory, surface renewal theory. Similarly, we will go to yeah. So like we discussed, Raoult's law, Henry's law, and some of the mass transfer theories such as two film theory, penetration theory, surface level theory, and Lewis Strickland theory, and how they are related to different equations. That is how the this film thickness, that is delta. So this delta is the film thickness. So how this film thickness varies with the or it affects the mass transfer between the two interfaces, and how this interface mass transfer theorems comes into account. So what we have shown here is that, so this is one of the questions, like it's been given in the assignments also, I think so, but it's much more related to what I've been already taught. So I just shown you mass transfer coefficient according to the film theory. What I've shown the equation is according related to the penetration theory. So this is one of the theory like two film theory. So the mass transfer coefficient is directly related to dAV by delta. The delta is the film thickness and dAV is the diffusivity of A with respect to B. So this is equal to diffusivity of A with respect to B. Okay. So now the question has been asked is that whether the mass transfer coefficient according to the film theory. So where in the exam also they will ask like different sort of questions. It's not just directly they will ask, but the theory they will write the particular point, that whether you want to relate it to penetration theory, surface renewal theory, and they can also ask in the terms here what they have, what is the mass transfer coefficient. In terms of mass transfer coefficient, they can also ask what are the various assumptions that has been made while deriving the two film theory or the penetration or surface renewal theory. So before arriving to the mass transfer coefficient's value or the particular formula, you must know what the assumptions has been made into that first of all. Because if you forget the assumptions, there is no meaning to go to directly to the equation and work out the equation and directly just tick in the final examination, because it will not help you out, because in a later point of time you have to know what are the various assumptions that has been made, because this all the assumptions has been interrelated with the final equation and how they are arrived at a final point of time. So it's better to go point by point, read each and every assumption specifically for each and every film theory and why they have made that assumption, and why this like different scientists have made different assumptions in order to arrive at a particular point of view. So it's better to go through each theories of mass transfer, like mass transfer theories. I have mentioned 4 different theories, and also Raoult's law and Henry's law, and how for Raoult's law also and Henry's law also there are various assumptions. So you must know what are the assumptions first of all they have made. It's not just like you remember the equation PA is equal to X into PA, or PA is equal to X into HL is Henry law constant. It's better to go what are the assumptions that has been made. So at later point of point, it will help you a lot, because while deriving some of the numericals or while solving some of the numerical solutions, you might know the equations, but you might not know what are the assumptions that has been made, because indirectly it will affect your numerical at some point of time. Because in some of the numericals you might have to make some assumptions And this assumption can already be built up in your mind if you have not the assumptions for the other scientists have already been made and arrived to a particular point of time. So what I will suggest is that better to go with every assumptions, read what assumptions and why they have made this assumption is one of the better point of view. Because if you just read what are the assumptions and just go to the final equation, that's everyone can do. So we are not going to do that here right now. So what we'll do is that we'll see what the assumptions has been made and how these assumptions are helping us to arrive at a particular point of an answer. That is the like various theories has been done. It doesn't take like 1 or 2 days to just write the assumptions. They have taken like years and years of time to arrive at a simple, well, simplified equation. But for deriving the simplified equation, they have made so much assumptions for that. So it's better to go for the every assumptions and look at every step of the derivation. So that derivations and the assumptions can help you a lot during the later point of time. Because I have done the same thing. I will go to the assumptions first. I will take look each and every step because in every step while deriving to a particular answer, they will use these assumptions in order to nullify some of the like numerical values or the derivation terms. So it's better to like simplify the derivation only by making the assumptions, and these assumptions can only be helpful if you have gone through all the lecture notes as well as the lecture videos. So it's better to go through each and everything with time. So we'll come back towards this. What we have been asking is that, like I showed for the penetration theory is root under DAB. So the two film theory is directly related to the diffusivity and the film thickness. But how it is been related? So if you go through the lecture notes directly, you can just point it out what are the assumptions that has been made for the two film theory. So it can relate the diffusivity by the film thickness. So it is inversely proportional to the film thickness. So the correct answer is DAB by delta. Okay, so what I will suggest, go through assumptions, being made to arrive at a particular specified or simplified equations. Okay, so this is another theory, like how the mass transfer coefficient according to the surface renewal theory is proportional. So the first one is the two film theory, and now is the surface renewal theory I have mentioned for the penetration theory. So now this is another theory. That the third theory I have mentioned is the surface renewal theory. So how it is related actually? So it's similarly the assumptions that have been made, and if you know the assumptions, everything. So like I've been saying, in examinations, MCQs will be there, but by looking at the question and the MCQs, if you don't know what is surface renewable and how they arrived at a particular answer, that's not going to bring any further help to you guys to grab the marks quickly. So like I'm suggesting again and again, go through the all the theories once more and try to find out, means, how these theories are interrelated. First of all, it's not just like that these are different theories we have to go through the course, that's why we are learning. No, these theories have some meaningful things in the real world also. So how these theories have been related and why they arrived at with this particular point of answer, why they did not arrive at some other point of answer, you can try to solve it out and get a feel of that, because that's getting a feel of that by solving by your own is a much more helpful as compared to just looking at the notebooks or the lecture notes and just try to solve that point of view. So forget about that. But what we'll do is that we'll go through the theories. Let's see how much you can just grab through the assumptions. And once you try solving the equations, you will know that these assumptions the scientists have been made. So I should take that assumptions and try to solve it out. And let's see what I arrive at a particular point of answer. Even though the derivations you will arrive by after simplifying so many terms using the assumptions will be different, but the thing is that you will try to have this habit again and again. Then at a later point of time, when you in the examinations, at some point, if you want to derive some particular, or you want to derive, or even if you want to solve some numerical or numericals apart from that, some derivations, then at that point of time, you have confidence like, yeah, I have made an assumption somewhere and I know how to make assumptions. So how these assumptions will help me out to try with a particular answer. So it's better to make assumptions at some point of time if they not have been given, but that assumptions will have a meaningful point like why you are making that assumptions. You also should have to mention that why you have made that assumption in order to arrive at this particular point. The first thing is that why you have made that assumption, and if that assumption is valid, you can proceed further by taking that assumption for a particular thing. So yeah, so this is what I've been saying. So like we see two film theory. Similarly for the penetration theory, I have shown previously in like before slides. So this is the surface renewal theory. So how the surface renewal theory is proportional to, like I said, is proportional to the diffusivity, inversely proportional to the film thickness. So this is one of the sort of the questions in the assignments also. So if you go to the mass transfer coefficient according to the surface renewal theory, it is proportional to the square root of the diffusivity. So these all are, yeah. So the correct answer is the square root of diffusivity of A respect to B. That is all. Now, so this is another point of view, how to solve at the various, like even in this question will help you out in the discussion problems also. So what is that is the degree of freedom actually. So the degree of freedom is how much points you need in order to derive a particular equation or derive a particular answer. So for a system at equilibrium, so just read the question properly. They have said that the system is at equilibrium and the number of the phases. So P corresponds to phase, C corresponds to the number of the components, and F corresponds to the degree of freedom is related to. Now, what is that? Oh, sorry. So if you consider F as phase, so the degree of freedom S is related to which thing directly? Okay, it's not showing. Yeah, now it's showing. Okay. So F is degree of freedom, N is the number of phases, C is the number of components, and F is the number of freedom. Now, if you can see, you see all the equations like F, C, P. There is another one term or the numerical term that is 2. We know what is F, that is degree of freedom. We know what is C, that is the number of components. P is the number of phases, and 2. So, at a particular point of view, if you try to solve out any problem in the world, or any problem from a theoretical point of view, there must be two different terms. Specifically, in general, there will be two different terms. And here we are asking for theoretical point of view because we are not mentioning this is a real world problem, but from theoretical point of view, if you consider as at equilibrium, what we say is that the two different terms, these two corresponds to the temperature and pressure. Okay, so these two are the two different terms that we are going to look forward. So if you can see the number of degree of freedoms, so this equation is very famous and it will try to help you out. So it is directly 1 mark, and apart from that, there are so many degree of freedom equations, also like 2, 3 different modes of type, which will include S and R also. That involves that thing will come later point when we discuss about the distillations and isotopic distillations. So that R corresponds to the isotopic distillation point of view. But we are not discussing, this is just the general formula of the degree of freedom, and F equal to C minus P plus 2. So this is the general equation for the degree of freedom in order to find out the number of unknowns in the like the problem which we have been given. Okay, so F equal to C minus P plus 2. So the correct answer is B. Okay. So we'll go to the next question and see which one of the following is correctly related the overall mass transfer coefficient. Yeah. So there are two different overall mass transfer coefficient. One is capital Kx and other is capital Ky. Okay. So these two are the overall mass transfer coefficients, and there are coefficients which are known as Kx and Ky. These are the local mass transfer coefficients. This is overall mass transfer coefficients, and this is local mass transfer coefficients. So which one of the following correctly relate the overall mass transfer coefficient Ky to the individual coefficients Kx and Ky? So like I said, the local coefficients or the individual coefficients you can mention, and the slope m of the chord of the equilibrium curve. So if you have seen these equations, so if I suppose if I plot y equal to x, and this is like the like like equilibrium line that is at 45-degree angle, and if you can see this is the curve, but what is the slope? Okay, if you consider it as a slope, you can take this. So this will be the steps going. This is not the slope, so this will be the slope actually. So how this slope m is related to this overall mass transfer coefficients and the individual coefficient, that is small k, small ky. So the correct answer, so there are two different equations which relates 1 upon capital Ky, 1 upon capital Kx, but all, if you can see that they have been asking related to the 1 upon capital Ky, that is the overall mass transfer coefficient related to the gas phase or the vapor phase. So this is the derivation. I am not showing the derivation here because it will another take half an hour for deriving at a particular answer. But it's just like quick point of view. If you have gone to the notes, it's just a simple point of view, and it's relates 1 upon capital Ky equal to 1 upon small ky plus slope m by 1 upon small kx. Similarly, 1 upon capital Kx is also there. Okay, like this one. So these are the two different overall mass transfer coefficients and on how they are related to the point. So now we'll go to one particular question. So how to obtain the relationship between the overall coefficients and the individual coefficients, like the local mass transfer coefficient. Like I said, I've directly shown the options, but now I will show you how to derive at a particular point of time. So we know that yi is equal to m into xi. This is I am getting it from the slope curve, like y equal to x, and there are equilibrium steps between them. And if you suppose Henry's laws is valid, then m is equal to h by p, where p is the pressure. So ya star equal to mxa, and ya is equal to mxa star. So these are the, I'm writing it further. And we know that the flux n equal to yab minus yai equal to kx xay minus xab equal to kx x star minus xab. Okay, or after simplifying, what I will get is that x star minus xab divide the flux of A divided by. So this is I am getting because of this loop, because I am just showing quickly. If you have seen this, this will be the slope, and you can relate this point and this point. Similarly, you can relate this point, this point, and this point, this point. So this is xab, xai, x star, that is equilibrium position, and you can similarly yab, this is yai and ya star. Okay, and here is an x and y. So the slope is, you can consider it this. This is the slope, that is m. Okay, so like I've been saying is that, so if you derive further, what you will see is that x star minus xab equal to x star minus xai plus, so I'm just separating it. Instead of xab, I have written xi plus and minus on both the sides. So it will give x star minus xai upon, by relating the above two equations, okay. Oh, sorry. And if you try to solve these things, like further verify, what you will get is that, and just write out here, 1 upon capital Kx is equal to 1 upon m double dash Ky plus 1 upon capital small kx. So this is how we derive the mass transfer coefficient related to the solids. Previously I have given it to respect to the ky. So this is with respect to the kx. Okay, so I'll show you that is ky1 I have mentioned up here and kx I have derived up here. So how to come at the overall mass transfer coefficient with the individual coefficients. Okay, so we will go further and try to solve out one of the numerical questions. So the thing is that these two mass transfer coefficients can also be related. Like the fractional resistance offered by the gas phase will be the resistance offered by the gas phase divided by total resistance on the two phases. Similarly, the fractional resistance offered by the liquid phase will be so you can write that easily just like gas phase and the liquid phase. So y will the gas phase, x will the liquid phase. Similarly, the fraction of the resistance offered by the liquid phase will be the resistance offered by the liquid phase divided total resistance of the two different phases. So 1 upon m kx divided 1 upon capital Q1. So like means I'm not saying that you have to mug up the equations and try to solve it out. So it's just like how you derive a particular point of an answer. Okay, so now we'll solve this question. So this is the question that I have taken from the lecture notes itself. Just 1 minute, guys. So this is one sort of a question that I've taken directly from the lecture notes. And if you see what has been asked is that for absorption of certain gas from air stream by water, the value of kg was found out to be 2 into 10 to minus 6 kilomole per meter square second into kilopascal. So the absorption that take place at room temperature, that is 298 Kelvin, that is 25 degrees Celsius, 25 degrees Celsius and 1 atmosphere, that is 101.325 kilopascal. So at a particular location of the column absorber, the gas phase concentration is 5 mole percent and liquid phase concentration is 0.2 mole percent. Like I said, that the counter current mode of the gas phase absorption of the gases, gas will flow from this side and the liquid will flow from the top to bottom. So it will be counter current absorption, which is not gas absorption column. So only 10% of the total resistance lies in the liquid phase. The solution obeys Henry's laws and the value of M. So slope is given by M equal to 1.5 at 298 Kelvin, that is room temperature, and 1 atmosphere pressure, that is atmospheric pressure. Calculate the individual coefficients, that is the local mass transfer coefficient, small kx, small ky, flux, that is Na, and the interfacial concentration. So we'll write what has been given. Capital Kg is equal to 2 into 10 to minus 6 kilomole meter square per second into kilopascal. Capital Ky is equal to, we can derive it as kg into Pa. Since P is given to us, so 2 into 10 is to minus 6 into 10, like 1 atmosphere I said, so you can write as 101.325 Pascal or 101.325 kilopascal. So I'm taking in terms of kilopascal because kg value is in kPa. So this comes out to be 2.03 into 10 is to minus 4 kilomole meter square per second. So now what they have said is that 10% of the total resistance is in the liquid phase and 90% of the total resistance lies in the so if 10% they have given, the remaining 90% will be in the gas phase. So the fractional resistance, like I said, fractional resistance offered by gas phase will be given by 1 upon small ky divided by 1 divided by capital Ky. So capital Ky divided by small ky. So since the fractional resistance is 0.9, capital Ky by small ky. So the local mass transfer coefficient with respect to the upper phase will be capital Ky divided by 0.9, and capital Ky we have derived over here is this one, that is 2.03 into 10 to minus 4 divided by 0.9. This comes out to be 2.26 into 10 to minus 4 kilomole per meter square into second. So this is the first answer. Okay, now what we'll see is that how the fractional resistance is obtained by the liquid phase. So what we have seen here is that gas phase. So this is first. Similarly, fractional resistance of the gas phase. Gas phase we have done, sorry, so we will go by the liquid phase. Okay, so it relates slope and we are by 1 upon capital Ky. Okay, and therefore 0.1, that is in the liquid phase is 10%. So we are written fractional resistance in liquid phase is 10%. This implies m by small kx equal to 0.1 by capital Ky. So this is one of the equation that we come through. Now we know that since we have derived the overall coefficient for 1 upon capital Ky is equal to 1 upon small ky plus m by 1 upon small kx. From this relation we can get m by small kx equal to 1 upon capital Ky from this equation minus 1 upon small ky. So what we will do, we'll put this here. Okay, so what will happen, therefore small kx equal to m upon m into capital Ky by 0.1. Therefore kx equal to, slope is given as 1.5 into capital Ky is 2.03 into 10 is to minus 4 divided by 0.1. Therefore small kx equal to 3.045 10 is to minus 3. Unit will be the same, kilos mole per meter square into second. So this is another answer. Okay. So this two what is solved is for the local mass transfer coefficient 1 upon capital Kx and 1 upon capital Ky. This is small kx and this is small ky. Okay. So now what they asked the flux actually. Okay, since I don't have the space, what I will do, I will just write directly the point here. So Na equal to capital Ky YAB minus YA star equal to 2.03 into 10 is to minus 4. YAB is given as 0.05 minus 3 and Y star is 0.3. So this comes out to be 9.54 into 10 is to minus 6. Then similarly, there is the flux is in kilomole meter square into second. Okay, so I will add one more slide here. Just 1 minute. Okay. Yeah. So how this is related? So we got Na equal to 9.54 into 10 is to minus 6 kilomole per meter square into second. That is the flux. Now we know that Na is been we have calculated. So what we'll do is that how to relate Na with the local mass transfer coefficients YAB minus YAB. This is for the gas flow counter current mode. Therefore YAB is equal to, or what we can do is that this equation is wrong, since minus YAB equal to YAB minus Na by small local mass transfer coefficients minus 0.05. So this YAB has been related to as YA as well. It's not the minus sign. And similarly 0.05 minus flux we derived as 9.451 into 10 is to minus 6 divided by small k we have derived, that is a local mass transfer coefficient with respect to the gas phase. So we have derived both the phases, but here we are taking some point of time in order to solve this one. So this comes out to 0.05 minus 0.042. So this comes out to 0.0078. So this is what is the flux of the species. So we derived kx, local mass transfer coefficients, kx, ky, and the flux also. Okay, so this is what this week talks about, specifically particularly related to the mass transfer coefficients as well as to the various theories of mass transfer. There is this two-film theory, penetration surface renewal theory, and Lewis Wickman theory. Apart from them, we have also seen the two different laws, that is Raoult's law of a mass transfer and Henry's law, that is particularly related to solid solvent, and whereas Raoult's law is related to the gas distance amount. So how to use these equations or these laws in solving the numerical problems. And apart from that, we have solved some of the MCQs what has been given in the assignments, and particularly because like I said, just not go to directly to the equation and mark the equations. At some point of time you might know what are the assumptions that has been made, so it's better go through the every assumptions that has been mentioned and then arrive at a particular point of time. Similarly, we have solved some of the numerical problems related to the countercurrent gas flow in order to absorb, like I said, countercurrent gas flow and how the slope of the line varies with the equilibrium curve, and how to derive like overall mass transfer coefficients and how they have been related to the local mass transfer coefficients of the individual coefficients. So the over has been represented by the capital, and the individual or the local mass transfer coefficients is usually represented by the small kx or small ky. That is the interface mass transfer coefficients in the gas phase and the liquid phases, and how they are interrelated to each other. We have derived one of the equation, and one equation and one of the question has been asked in the question that I've showed with the help of the MCQ. And similarly, we have used these two different equations which relates the overall mass transfer coefficients and individual coefficients to arrive at a particular answer by looking at this question. So this is one of the set of the questions which can be asked in the final examination. So what I will suggest is that go through the lecture notes again, revise it thoroughly, and try to solve it out some of the numerical problems not in the assignments. Once you are done with the assignments, try to solve some of the numerical problems from the standard books, standard different books like uh, Robert E. Trebal, that has been given as a reference books for this course on the NPTEL 7 portal. So I will suggest this, guys, it's a very good book, and most of the undergrads will follow that book for this mass transfer operation course, which is generally the core course of the chemical engineers. So it's better to go through Trebal. As mentioned, there's a reference books on NPTEL, and there are so many unsolved numericals after every chapter ends. So you just try to solve it out. Even if you get wrong, you will you will get an idea at which point you are getting it wrong, because unless and until we try to solve it, we don't know at which point you are having right now. So it's better to solve unsolved after assignments has been submitted. Try to solve it unsolved numericals solution problems, and try to get a feel what we have learned through the lecture notes or the lecture videos, and what we are discussing we are discussing here in the online interaction. So it will try to help you guys help a lot during the final examinations also. So this is what I have for today, and I would like to say, if you have any suggestions, I have been saying from the past 3 weeks, I'm saying in the week 4 also, please do let me know which particular problems you wanted me to solve, because as soon as this course progress, the difficulty of the course will also go up, because there are so many different concepts that are about to come, like the distillation columns, gas absorptions, leaching, extraction, uh, LLE. So it's better don't to like compile all the things which we are not going to like week 1 to week 4, because all these weeks will be compiled and be taken as a final examinations. So it's better to go through each and every lecture notes, videos, as well as this live interactive sessions, and try to solve out some of the unsolved numerical problems. If you face an issue during the solving, just let me know. During this live interaction, you can try to solve it out at the same point of time. Apart from that, you can also mail on the NPTEL SWAYAM portal. There is a feedback form or forum on the NPTEL. You can post their problems there also. So if anyone has problem, they can ask the question. If no one has any questions, we will meet next weekend on Saturday at the same time from 3 to 4 for the live interaction for the week 5. So we'll try to solve out some of the numerical problems. Similarly, what we are trying to solve out every weekend. Before that, I will just proceed what the concept that has been taught in the class. Like we are going throughout every day. Sorry, every week. So I will try to gather as much as like quickly 5 to 10 to 15 minutes for the concepts for the course week content, and then we'll try to solve out some of the numerical problems. Similarly, what we are trying to do from the point of time we started these live interactions. So thank you very much for joining this live interaction, and we'll meet you next week at the same time, Saturday 3 to 4. If no one has any question, we'll meet you guys next week. Thank you guys. Thank you so much for joining. So thank you guys. We'll meet next week, 3 to 4, at the same time, Saturday. Thank you guys. Thank you so much. See ya. Bye bye.